thought I would bend your ear about enzymes for a few minutes, and if we could have the slides. Oh, here we go. So I am trained, actually not as a chemist, the chemist will tell you that. I'm trained as an engineer, and I became an engineer in the 70s because I wanted to work on the most complicated things on the planet, which I thought were spaceships and airplanes. And then I found out when I became a chemical engineer that in fact the most complicated things on the planet are proteins and cells and organisms and ecosystems. I fell in love with these marvelous molecular machines called enzymes that do all the chemistry of the biological world, taking simple, abundant materials like carbon dioxide, sunlight, and turn those through chemical transformations into trees, into you, into me. That's chemistry that no human being can mimic or master. And it's chemistry that the best chemists on the planet developed, and that best chemist is nature. So I decided to become an engineer of the biological world, to build enzymes that would not just serve the organisms that invented them, but that would serve me in our purpose, that would serve us in our purpose to live sustainably on this planet. If we could build new catalysts like this to do things for us, we could use the power of biology to transform those abundant materials into what we need in our daily lives. No one knew how to do this, however. No one knew how to recode a protein at the level of the DNA in order to create something useful. Of course, this field was owned by structural biologists, and they looked at it from their point of view. Let's get a three-dimensional structure of the enzyme and then go in with your big brain and make changes. And of course, that didn't work. It didn't make things that were better. It was called protein terrorism. So I turned to the process that made these molecules in the first place. And it turns out that nature is not just the best chemist, and of course she's all of the biologists, she is also the best engineer, because she invented this incredible process called evolution. So that's what I turned to. And here, this process, think about it, is just a simple algorithm of mutation and natural selection, right? That's given rise to all the diversity of the biological world. Everything complex in this room was made and invented and innovated by evolution. So it seemed obvious to me that one should use this same process to create the enzymes of the future. Let's just think about it. We heard a lot about the universe just a few minutes ago. Well, there's a universe of possible biologies out there, and literally many more possible protein sequences, for example, than there are particles in the universe by many orders of magnitude. There's an enormous space of unexplored biology that nature's never had a chance to access. So all of you biologists, you live in that little green space there of things that have been explored by natural evolution, a lot of them thrown away, but others kept. My space as an engineer is all of the universe of biology. And out there lie enzymes that will cure cancer and proteins that will solve the energy crisis. There might even be the cure to death and taxes. And we want to find that. So that's the challenge. How do you use evolution to get outside of the green box and explore possible chemistries and biologies that might be useful to humans? Now, if you look at it from the practical engineering point of view, and that's what I had to do, was translate this vision into something that would actually work on a time scale that's relevant to a PhD thesis or getting tenure at a university. And so it becomes, you can think about it as an optimization problem. And of course, it's thousands of dimensions. The number of ways that you can change a protein sequence to recode its DNA is enormous. And if the fitness landscape, that is what I want this enzyme to do, let's say new chemistry, or work under industrially relevant conditions, if that fitness landscape is rugged, right, like on the left, then you make changes to the sequence and it falls into a crevasse of non-function and evolution stops. And clearly evolution has not stopped. We are all the products of evolution. So that tells me, and it told people smarter than I who thought about this problem some years before, that the landscape has to be somewhat smooth in its many dimensions. It's more Fujiyama-like on the right. And if the landscape is smooth, any fool can optimize on that because you just close your eyes and keep walking uphill. And that means you can implement evolution as an algorithm, a simple process of make mutations, see what works, and accumulate those over multiple generations. So that's what we did already 35 years ago. We could use the then tools of molecular biology, and they're so much more powerful now, to take what nature had given us, some enzyme that was sluggish or didn't really want to do what we wanted it to do, but it had a little bit of measurable activity, and you ask it to do something new, right? You ask it to do the red job, it's generally less enthusiastic. Function drops. And that's what we had to deal with in the past. But if you implement evolution by artificial selection, where I decide who lives and who dies and who goes on to parent the next generation, basically breeding enzymes like you breed cats and dogs, you can push it back up a new peak by directing its evolution. And that was the basic idea that we were able to then implement in the laboratory, and I don't have time in this brief discussion to go through the methods, but they're all well known to anybody who does molecular biology and microbiology. But that enabled us to start thinking about what is a future of chemistry, clean chemistry done biologically, encoded in DNA, where nature already knows how to use abundant resources, waste products, agricultural wastes, garbage, sunlight, and then convert those not into more organisms, but into the products we need in our daily lives. And because this is a session about innovation, and innovation leading to, I hope, prosperity, I'll just give you a few examples of what students from my group have done over the years, using enzymes evolved in the laboratory to make everything from jet fuel. We could make isobutanol in yeasts and convert that into jet fuel. That became a publicly traded company in 2011 and is still in business. As far as I know, they don't make any money because oil is cheap and waste products are still expensive. But if we ever put a price on carbon, this technology exists and it works really well. Just recently, before the pandemic, we started another business making intermediates and non-canonical amino acids that go into something like peptide drugs, for example. These are made by 7 or 8 really dirty chemical steps in very expensive processes. But with the appropriate enzymes, and we evolved these in the laboratory, you can make hundreds with a single platform, all tuned to make different products. And this now is one of the only US domestic suppliers that can supply at scale to almost all the major pharma companies. And then I'll just give you, this is just to show the spectrum of applications. If you can convince biology to work for you, in 2014, former students of mine also started a company in crop protection, where you want to replace toxic pesticides used all over the world to combat pests like this fall armyworm that has devastated corn crops from Mexico to Kenya to China. And this pest is resistant now to pesticides. Yet if you spray, so imagine this, how do they mate? If you can interfere with their mating mechanism by spraying a little bit of the authentic insect pheromones, or her Chanel number 5, so to speak, she emits this plume of pheromone, and he flies around and finds her. But now imagine you spray a little Chanel number 5 in the field, and I'm talking gram quantities. Suddenly they're totally confused, and the males can't find the females, and they don't mate. Completely non-toxic, extremely effective, and now this product that Provivi makes is used all over the world. They just supplied a 700,000-acre farm in Brazil, where the pest pressure is just enormous, and even the genetically modified crops are starting to develop resistance to these pests. Those are just examples, and there are many, many more. You may not realize that many of the products you use in your daily lives, from your laundry detergents to reagents you use in science for DNA sequencing, to the processes that make your pharmaceuticals, all use enzymes that have been optimized for these human applications by directed evolution. And that got me the greatest accolade of my life. When I was asked to go down to Burbank, in Warner Brothers Studios in Burbank, and appear on The Big Bang Theory. Now, Tom, I know you're going to talk about science communication. Let me tell you, you cannot begin, I go all over the world and give talks as a Nobel laureate. Many, many, many more people have watched The Big Bang Theory that know anything about what Nobel laureates do. But they love the idea of nerdy graduate student scientists who are becoming, over 12 seasons, extremely annoying professors who are now lobbying for Nobel Prizes. So I got to be lobbied, and my contribution was to take Sheldon's oatmeal raisin cookies and throw them in the trash can because I wasn't going to be bribed. But that was a lot of fun, and I learned a lot about science communication from that. I also got invited to a great party. 2018, I have to tell you, they do such a good job in Stockholm. It's cold and dark and miserable in December, but it's a great party. If you get invited, you have to go. That's all I'm going to say about that. You really should go. So let me just spend a couple minutes at the end to tell you about innovation. Because I've told you about optimization. You take something that exists and you optimize it. And I did that for many years. But more recently, I decided I was going to do something I thought would be much harder. And that's to truly make something novel. Some chemistry, for example, that nature never explored, using mechanisms that are unknown in nature. And I was annoyed because other Nobel laureates like David Baker were designing really terrible enzymes, but they could do chemistry that nobody had ever found in a database, and you didn't know where to start. And then I realized I was thinking about it all wrong. That nature, if you think about it, nature is making new enzymes all the time, often in response to pressures that we are placing on the planet. But she's doing it, and to make a long story short, she's doing it very much the way that I just described to you, where enzymes that exist today have a function that's under selection, but they have multiple capabilities. They're like graduate students, right? Graduate students are selected for their ability to work long hours at low pay, but they could do other things. Enzymes are just like that. And due to the huge diversity in the biological world, when an enzyme encounters a new challenge, if it can do it, it becomes the fuel for further evolution. So that means that for me as a breeder, I have to recognize these inherent capabilities that already exist within an enzyme's active site, and then draw that out through this process of just turning the crank, algorithmic process. So we were able to, this is my favorite example, so I'll just give you an example to expand your thinking. No one ever found carbon-silicon bonds in biology. 50 products in this room made with carbon silicon bonds using dirty human chemistry, never found in nature. So we said, okay, let's make an enzyme that forges carbon silicon bonds. Because what will that do? Well, it probably won't do anything useful, but it will open people's minds about what biology could do. So it becomes what enzyme or what protein that exists today, or that I could design, might be able to do this. And here you just use a little bit of human chemistry as an inspiration. And so there's enzymes out there that can activate oxygen, forming a reactive oxygen species. And if you're a chemist, and you squint hard enough, that looks like a reactive carbene. They're very similar chemically, structurally. And so we said, okay, let's just go see if iron heme proteins using iron, earth-abundant metal, were not iridium or rhodium, which human chemists use. Could it use this iron heme to activate a carbene and transfer that into a silicon hydrogen bond? Carbene transfer. And the answer is yes. There were proteins out there that could do it. And because this is short, I won't be able to give you all the data, but let me just tell you, when we reported this work, no one read the paper. Absolutely no one read the paper because it was 130 pages of supplementary information. It was a really boring chemistry paper in Science magazine. But they all read this article that Bob Service did, and you can see he also used Star Trek to, you see Captain Kirk and Dr. Spock in the Horta episode when they're looking for life in rocks. They were able to capture people's minds, and that news, when we published the paper, went all over the world. And it mutated as it went, so that by the time it hit the UK Daily Mail, we were putting silicon chips in people's brains. But so the communication wasn't very clear, but it did exactly what we wanted it to do. Now people realize that biology is not there just to do what we chemists and biologists find in nature, but it's poised to do so much more. And the novelty, if you learn how to use evolution for forward design, that novelty, that innovation comes from the diversity that exists, but it's poised to solve many more problems. So for example, Dow Chemical came to me after we published the paper and gave me a lot of money to try to figure out how do you not only make these bonds, how do you break them down? Because silicones, siloxanes, are accumulating on the planet, and they're billions of pounds made every year, and they're non-biodegradable. And some of them are considered to be toxic. And so just last year, we were able to make not only the first enzyme that makes carbon silicon bonds, but the first enzyme that breaks carbon silicon bonds. So now you can think about this human chemistry in a circular fashion. And I'll just end by saying, this is more of a joke, but half my group now does machine learning and AI. Because where does that fit in? This is an algorithmic process of active learning, basically. And we generate a lot of data. So already starting 15 years ago, we started applying machine learning to speed up the process. And you can imagine, if you know anything about David Baker's work, if you want to have a starting point for new chemistry, artificial intelligence is a great way to do that. And you combine these. And we've also heard about laboratory automation just very now. So if you can automate every step in the process, which you can, we can actually work towards just pushing the button to get any catalyst that you want. So I want to genetically encode all of chemistry. And of course, my graduate students love that idea. This was posted on Twitter on April Fool's Day, but it is, a few years ago, but it is very far from being an April Fool's joke today. This is really true. I just want to end by saying I spent 4 years volunteering time to assist the president in science decision-making, and it was an extremely wonderful time because we had a president who was interested in the advice of scientists, and we had a fabulous group of people who contributed to this So there I'm telling him that AI is scraping the Library of Congress and the internet and probably his bank account. And he says, they won't find anything there. But I'll just end with these words, because when I was rolled out and introduced to the country in January of 2021, in binary code on the wall. Anybody here read binary? Well, I will just tell you that in the code on the wall there reads hope over fear, unity over division, science over fiction, truth over lies. That's what science can do for us. Thank you.